Hey guys, welcome. Yeah, so in this video we're going to talk about the remainder theorem and understand why it works, because, well, that's what's fun, right? And of course I'm going to give you, as usual, a couple of concrete examples. The remainder theorem is something that is first taught in a high school algebra 2 course, but we're going to discuss it here at a sophisticated enough level and bring a couple of college level ideas, and so you'll get a lot out of it even if you're not a high school student. Yeah? Okay, cool. All right, so let's get on with it. Now, if the task in both of these problems is simply find the remainder, then we don't have to use the remainder theorem. We have a couple of other options, specifically synthetic division and long division. We can do synthetic division on both or long division and then find the remainder that way, right? Now, if you have the option of using synthetic or long division, you should use synthetic division. Now, we know that long division always works. That's the benefit, but it's cumbersome. Synthetic division doesn't always work, but it works in these two cases, so I'm going to do synthetic division in both of these problems. Now, of course, I would just get to the remainder theorem, but to explain the remainder theorem fully, I need to do synthetic division because I need not just the remainder but also the quotient in these two polynomial division problems. Yeah? Okay, cool. Now, if we do synthetic division on the first division problem, then I'll keep it a little bit of a mystery so that you watch my awesome many videos on synthetic division. Yeah, that's an ad. But yeah, so watch those if you need to see lots of examples on synthetic division. But I'll do it quickly here as I said, and so here we are. This is how it would go. So the remainder in this first polynomial division problem is 11. Yeah? Okay, cool. And we have the coefficients of the quotient as well. So what we get out of looking at this is that when x squared plus 3x plus 7 is divided by x minus 1, it's equal to x plus 4. I'm laughing at a real inside joke. And then it's the remainder divided by the divisor. That's how we always write it. We write the remainder divided by the divisor. And so that's that in the first problem. So yeah, like we have other options that are pretty quick, but the remainder theorem is very powerful in a lot of instances, and it's possibly even quicker than synthetic division. Okay, so in the second polynomial division problem, this here, we write a minus 2 here, and then we account for any missing powers of x with a 0 placeholder, so a 0 there for the missing x cubed term, and then minus 3, and then 4, and then minus 12, and let's extend for the minus 12, yeah, okay, and then 1, right, and then negative 2, 4, I'm saying right like you can respond, 1, and then, but I was saying right, okay, no, alright, now I'm clowning too much, yeah, 2, and negative 4, minus 16. Now, yeah, I re-recorded an awesome video, just like this one, but I added wrong here, and that's one of the reasons why I had to re-record. But yeah, also what it means is that in this division problem, x to the 4th minus 3x squared plus 4x minus 12 divided by x plus 2 is equal to, let me write this minus 16 just above it, because we need the space, I anticipate, it's equal to, well, the coefficients are given right there. It's x cubed minus 2x squared plus x plus 2, and then plus the remainder, which is plus a negative 16, all over the divisor. I'm running out of space, obviously. X plus 2, right, all over the divisor. X plus 2, like that, right? Okay. So we'll need that, but we no longer need this But again, the remainder in this first guy is 11, and the second guy is negative 16. Okay, now let me make sense of why the extra work. Okay. So, this should help you understand why we have to write the remainder and the way that I have written it, which is write the remainder divided by the divisor. And that is, well, what we're going to do next is multiply both sides of this equation by x minus 1. When we do, this is what we're going to be able to write. We're going to write x squared plus 3x plus 7 is equal to, remember, we're multiplying both sides by x minus 1, so we're going to get x plus 4 times x minus 1, and then plus 11. Right? I've multiplied both sides by x minus 1. And if we do the multiplication by x plus 2 on both sides of this second guy, what we're going to be able to write is x to the 4th. What I'm writing is super important. It's really cool. I'll show you. X to the 4th minus 3x squared. Or am I just selling you? No, it's really cool. Like, you'll appreciate it. 4x minus 12 is equal to, and it's going to be x cubed minus 2x squared plus x plus 2 times x plus 2 and then plus a negative 16 plus a negative 16 like that. Yeah, okay, whatever, buy that chalk. Okay, all right, yeah, okay, cool. This is really important. This is really cool. And I'm not just saying that. You'll see. Okay. So, let's do this. So, this here, what you see here, is what's called the division algorithm for polynomials. And so you can study it at an advanced level in abstract algebra in college. But yeah, I'll say a little bit more about it. But first, let's use this segue. So suppose I have 7 divided by 3. Well, I can write that as 2 plus 1 divided by 3. And notice that this here is analogous to what I erased. And now I wish I didn't erase it. Which is, we had, like, in this case, we had x squared plus 3x plus 7 playing the role of just 7 here. And then divided by, we had x minus 1 equals, well, the quotient was x plus 4 plus the remainder 11 divided by x minus 1. That's exactly, like, analogous to this here. Now, what I did once we had that over here is I multiplied both sides by the divisor, which in this case is 3. So then what I'd get is that 7 is equal to 2 times 3 and then plus 1. So what we have is that specific integer p can be factored in this manner, which is written as the quotient, let's call it q, times the divisor plus a remainder. And what has to be true is that both the quotient and the divisor are smaller than p, but that in turn the remainder is smaller than both the quotient and the divisor, right? That'd have to be true, and the numbers here clearly say that. And you can do it on infinitely many other numbers, and you'll consistently find that the remainder will have to be smaller than these two guys, and these two guys would have to be smaller than that. Okay, cool. And that's pretty much exactly what we have here, because, like, well, 7p is played by this polynomial here and that polynomial, and then our divisor is, well, in the one case x plus 2 and in the other case x minus 1, and then the quotient, so that's this cubic and then that linear, and then of course a remainder. Okay, now look at what has to be true when we compare the quotient and the polynomial. The quotient has to be 1 degree less. This is a quadratic, this is 1 degree less. This is a quartic, this is a cubic, 1 degree less. Yeah? And the remainder has to be a degree less than both the quotient and the divisor. And since our divisors in both cases are linear, then the remainder has to be 1 degree less than a linear, which is just a constant, right? Okay, so what I said, which is the analog in the polynomial world to this division algorithm for numbers, is the division algorithm for polynomials, which goes something like every polynomial p of x can be written as x minus a times a quotient q of x plus r. Now, the more general division algorithm for polynomials that you'll study in abstract algebra will have r of x. Because, well, if I was dividing by a quadratic, say I was dividing a quartic by a quadratic, then it's possible to have a remainder that has an x in it. But since here we're dividing by a linear, and we require that our remainder be of 1 degree less than our divisor, our remainder will have to be a constant. So I could just write it as r instead of r of x. But again, more generally, you write it as r of x. Ah, cool. How useful. Because, well, if this is true about every polynomial, which is if we can take every polynomial p of x and be able to write it in this way, well, then look at what would happen if we evaluate at x equals a. P of a is going to be a minus a times q of a plus r. But wait, who cares what q of a is? A minus a is 0. So this whole thing here is 0. So we get that p of a is equal to r. So you see, first, I showed you that if we're dividing p of x by x minus a, that we could manipulate it and write it as p of x equals x minus a times some quotient plus a constant remainder. And then if we plug in a into this version of p of x, then what we're going to get is that p of a is simply r. So that is the remainder theorem. It says that when a polynomial p of x is divided by, when p of x is divided by x minus a, the remainder r is equal to p of a. That's basically, this here is in a nutshell what the remainder theorem says. Yeah? Okay. So, in this case, since what we're dividing by is already written in the form x minus a is 1, and so p of 1 is going to be plugging in 1 into this quadratic, which is 1 squared plus 3 times 1 plus 7, and that best be 11. And it is. And in this case, since x plus 2 is not in the form x minus a, we first write it as x minus and negative 2. And now it is in the form x minus a, so a is negative 2. And so p of a is p of negative 2, which is negative 2 to the 4th minus 3 times negative 2 squared plus 4 times negative 2, and then minus 12. And believe it or not, I re-recorded this video like probably 16 times, and so for that reason I'm not gonna like do the arithmetic with you. Like, you can check it, it's good. Yeah, okay, cool. I hope you enjoyed this and keep watching. Take care.